Hi, welcome to this session by Root Fabric, and in today's session we're going to be covering Introduction to Java. Before we start, I just want to preface that this is going to be a completely beginner level video. So if you don't have any programming experience whatsoever, that's fine. We're going to be going over everything. So that means that if you do have some programming experience, this might be a little slow for you, but I just want to make sure that we get down all the basics behind it first before we jump into any code. And generally, the better you know the theory behind computer science and the theory behind programming languages, the more successful you're going to be at programming in them. All right, so the plan for today is we're going to go over some basic computer science just so we know what we're talking about. And then we're going to discuss programming and languages in general, and then we're going to talk about how Java interprets code, and then we're going to get into some specifics with Java. But we are not going to be coding at all today. We're going to save that for later. All right. So first, before we can code anything, we need to understand how do computers work. So a computer is made up of a few different key parts. So you have a processing unit, so that's your central processing unit in a computer. You have memory, and then you also have permanent storage. So first we're going to be going over computer processors. So computer processors do all the calculations for all your programs and software. So modern processors today are made up of billions of tiny switches called transistors. So every processor can be broken down into just a sequence or a structure of tiny switches called transistors. So these transistors only have two different states. They can either represent on or off. So generally, in computer science, we consider the on state to be a 1 or the off state to be a 0. So because of this, processors can only understand data and operations in a binary format. So that's ones and zeros. All right, and then processors can only read data if there's somewhere to put that data. So that's where memory comes into play. So memory holds data for our processors, again, in a binary format it can understand. So whenever you're running software or anything like that on your computer, the data that software is using is stored on your memory. And memory is going to be the fastest storage that your processor has available to it. So this is where most of your data in a program is going to go. So the processor is given commands by the software we use to create data, move data, or change data in some way. And most of this is done in the computer's memory. So processors today are made up of a list of instructions they can do. And when we write a program, really all we're doing is we're telling the processor, do this, do that, then do that. If this is true, do that, that kind of thing. So all programs can really be broken up into a long, complicated list of instructions to a processor. And really, most of these instructions, the amount of instructions used is pretty small. Like modern processors today can support x86 processors can support like I believe it's like 95 different instructions. So that's not very many considering everything you can do with software on a computer. So the memory that your computer uses is broken up into many sectors, such as the stack, the heap, and the code segment. There's more, of course. We'll discuss this further later. It's not particularly relevant right now. You just need to know that there's different sectors that exist. So memory is volatile, meaning that it is completely clear when power is cut. And you can see this, when you use your computer. If you don't save a file or something like that and you cut off the power, that data is going to be lost. And many programs will store temporary things just in the memory. It's not all going to be written to some storage. All right, so if memory gets cleared with every power cycle, how do we store data between reboots? Well, this is where storage comes in. So storage is going to be permanent data holding. So storage is much slower than your computer's memory, but it can also hold data indefinitely. So any file that you put on a computer's hard drive or a computer's solid state drive will stay there for a long time. It won't go away after a reboot or anything like that. So this is where files and programs are stored, whereas the data a program creates while it is running is stored in the memory for faster and easier access to the processor. So when you're running your program and a new variable is created, or maybe a new structure is created, that kind of thing, that is stored in the memory. and then it's moved around from the memory and things like that as well. So again, as I said, at its core, all data is in a binary format. So this is the only format that computers can actually understand. So this poses a pretty big challenge for computing today, because how can we, as humans who have abstract thoughts, talk to a computer that can only understand things in a binary format? But it is good to know that this format can really represent any data with enough ones and zeros. So, as humans, we generally think in a base 10 kind of format, but you can represent base 10 numbers in ones and zeros if you have enough room for it. So, because of this is how we're able to have files such as PowerPoint files or readable text files. It's really just a sequence of ones and zeros, and if you have enough ones and zeros, you can really represent any data. So then, how do we talk to computers? So, like I said, computers can only understand a binary format, so how can we effectively communicate with them? Well, in the early days of programming, programs were written directly in binary instructions to the processor. This is called machine code. So we could do it this way, and we could talk kind of directly to the processor, but the biggest issue with this is that this is very tedious. It's not very intuitive at all because we don't think this way naturally. So today we are able to use things like programming languages to talk to computers. And it's very important to keep in mind that programming languages themselves are not readable by computers. So if you write a source file in, C++, Java, C, whatever it may be, the computer can actually execute and read that source file. Programming languages exists for us to understand and make it easier to talk to the computer. So they're not really aimed around the computer. A lot of people think, programming is difficult and hard to understand, but really programming is designed to make it easier to understand how to write software. So our programs are written in a language, any language, and then these must still be converted to a binary list of instructions. Like I said, this is called machine code. So there's a few different ways you can do this, and we'll talk about some of them. And then, as I stated, keep in mind a programming language may seem difficult, but it is infinitely easier to understand a programming language than it is to understand raw binary machine code. So it really is a tool for our benefit. So if you ever feel discouraged or you feel like it's difficult, just keep in mind that it is much easier than it could be, and that this is a tool for our disposal. All right, so programming languages. So if a programming language cannot inherently be read by a computer and needs to be converted to machine code, how do we do this? So generally there are two main methods to turn a language into executable machine code. So there's compiling and then there's interpreting the code. So we'll go over each for a little bit. So compiling a source of some language means you run it through a special program called a compiler, and basically what this will do is it'll go through your code, it will read and understand your code, and it'll turn it into machine code. And usually along the way, it'll make some changes for you, like optimizations to make your code run faster, that kind of thing. Um, then you also have interpreting. So while compilation turns a program into machine code ahead of time, so when you compile a program, you write the program and then you compile it, and then you can run it after that each time without needing to compile it again because it's already been turned into machine code. Well, interpreting does this in real time through a program that can run your code called an interpreter. So Java is a mostly interpreted language. Really, there are very, very few languages that are completely interpreted because generally interpreting a language 100% is very inefficient. So what Java will do most of the time is it'll go through your code and it'll compile what it needs to compile very quickly before the code is run, and then the rest it'll interpret while your code is running, and we'll go over how all that works. So I'll just go over some pros and cons of both. So since compilation results in direct machine code ahead of time, these programs are generally faster and more efficient for a processor to execute. So since your program, your executable, is written entirely in machine code after it's compiled, your processor doesn't have to think about anything. It just goes straight to it. There's no middleman. Um, So this is both a pro and a con, really, because since these are turned directly into machine code, This means that this machine code might not work on every processor, especially processors of different architectures. So your processor has a set of instructions it can execute. Your machine code is basically telling it which instructions to execute. Well, if a different processor has a different list of instructions, for example, your phone processor has a very different list of instructions than your desktop computer processor, then you're going to run into a problem because your processor is not going to know what to do with this machine code. It's going to look at it and it's going to say, I don't know what any of this means, and your program isn't going to work. So this is why even today we have limitations on our applications. So like on our desktop computers, we cannot use the same exact applications that we can use on our mobile phones. So to get around this, a lot of developers have to rewrite an application for mobile or the other way around. So basically, I can't open up my iPhone or my Android phone or whatever and run PowerPoints on there because that's a desktop application. But if Microsoft makes a version of PowerPoint for mobile and they rewrite the entire application, then we can do that. So this is where interpreting comes into play. So while interpreting is much slower because it's done in real time as the program is being run, it can be much more portable. So since the code doesn't rely on a compiler and it's not changed into machine code ahead of time, basically all we need is an interpreter present on the system and the code can run. So in Java, the interpreter that is used is the JVM. So basically, that's the Java virtual machine. Basically, what that means is as long as there is an instance of the Java virtual machine available on a system, you can run the code. So this is why you're able to run code like Java code on a phone, on a computer, even a smart refrigerator can run Java applications if it's able to run the JVM. So it makes it much more cross-compatible, and this makes it much easier for the developer too, because now we don't need to go back and rewrite an application for another system. We can use the exact same code and put it across multiple systems, and that saves everyone a lot of time. So let's talk about the JVM. So the JVM is very important to understanding how Java works. So the JVM is the Java Virtual Machine, and this is the Java language's interpreter. So whenever you make your code, this is what your code is going to be running through. So this is what's actually going to be reading through your code. Whenever you get any errors or anything, it's going to be from the JVM. So it's important to note that there is not one universal JVM, but there are actually many different JVMs, but they all conform to the same standard and they should be cross-compatible with any Java code. So it doesn't matter if you have Oracle's um, Java runtime environment or you have, open Java runtime environment or maybe some third-party Java runtime environment with a JVM present. It shouldn't matter. They should all conform to the same standard and they should be cross-compatible. So generally, you don't have to worry about this. But there is a few things that you should worry about, especially when you're making larger projects, I should say. So as long as the JVM is present, your Java code can run, but there are a few caveats. So the instance of JVM must support the Java version you're using. So an example of this is a lot of older systems still to this day have a JVM that only supports up to Java 8. So if you're writing your code and you're writing it in the latest and greatest release of Java, let's say Java 14 or whatever, and then you try to run it on a system with an older JVM, you're going to run into a lot of problems and it's not going to work. And then on top of that, not only is it not going to work, but since you've been using features that were in the newest version of Java, you're going to have to fundamentally change the way you're looking at your code. So you're going to have to go back and you're going to have to change how you're doing things because those exact same features might not be available on an older version of Java. So this is why for large or important projects, you really want to use a long-term support release of Java to ensure that it's going to be compatible with older systems or that kind of thing. And if you're ever curious about this, you can just go to Oracle's website and look at the versions of Java and go over which versions are LTS and that kind of thing. It's also important to note that the newer versions of Java that are not LTS are also not supported for as long. So you may be uprooted really quickly. Let's say a project takes a couple years or that kind of thing, and you're using a new version of Java, you might have to switch halfway through your project. So that's also another incentive to use a long-term support release of Java for big projects. All right, so how do we actually write code in Java? So there's a few different ways you can do this. You can use an actual text editor. like some people do, or you can use something that's called an IDE. This is what I highly recommend, especially for Java. It makes a lot of sense in Java. So an IDE is an integrated development environment. So basically what this means is that it gives us a place where we can write our code, set up our projects, debug our code, and run our code all in one application. So this makes it really easy for us, and this especially makes sense for Java because the code that we write in Java is not compiled. It's run through a JVM, so there's no reason really to split up the running process and the writing process because it's going to run through the JVM either way. So an integrated development environment, IDE, makes this much easier for us. So in order to code in Java, we must understand the syntax of Java. So what's syntax? So this is basically the formatting of the language. So this is how the JVM expects Java to be written. So a lot of people, when they first start coding in a new language, or if it's their first time coding in any language, they get really caught up on the syntax, and it can be confusing. But the reason we have syntax and the reason it exists is that it really empowers the programmer to make sure that the language we're writing in does exactly what we want it to do. So when we program a piece of software, we want it to follow what we do exactly. We don't want any variation. We don't want any potential for it to mess up, that kind of thing. So syntax for some people might be, the bane of their programming, but really it's for your benefit, and you want syntax to be strict sometimes so that you know that the JVM knows that it's doing exactly what you want it to do. So if you think about it, really all languages have syntax, even English. When you're writing in English or you're that kind of thing, you people expect there to be commas, they expect there to be spaces in between words, they expect you to capitalize proper nouns, that kind of thing. And if you weren't to do that, then your message would be misinterpreted. It would be very hard to tell what you're trying to say. If you go online and you're reading an article and imagine there's no paragraphs, no punctuation, no spaces in between words, it's just one big block of text, you're not going to be able to understand that very well. So, syntax is actually a very good thing for understanding. So, the best way to get good at understanding syntax in Java or any language really is to practice a lot. So it might seem difficult now, but the more you practice, the more it's going to become like a second nature to you, and then it's going to get easier and easier as you practice. So, all right, programming in Java continued. So errors. So what is an error? So if we use the wrong syntax or we attempt an impossible operation, an error will be thrown. So we can see, so the nice thing about an IDE is we can actually see the errors as we're writing our code. So we'll be typing away our code, and before we even run it, it'll tell us, hey, this is going to cause an error and your program's not going to run. So we can see this in real time as we're writing our code. So errors will prevent our program from ever running. So if our program has an error in it and we try to run it, it's not going to work. So it's important to note that errors are not the same as exceptions. So if you have an error, your program will not run at all. But if you have an exception, your program can run still until it encounters that exception, and then it'll kill your program unless you handle that exception. And we'll get into that later on. But these are different. So either way, if you see one of these, it's important to go back in your code and see what you did wrong. A lot of people, when they get errors or they get exceptions, they think, oh, there must be a mistake. Maybe there's a problem with the JVM. But the fact of the matter is that Java is a very, very robust language, and most programming languages will do exactly what you tell them to do. So it's important to go back, review your logic, and really ask yourself the question, what am I telling the program to do? And go through it line by line and analyze, am I telling it what I want to tell it? Because a lot of people have this idea in their head and then they'll code and they might not necessarily line up. So that's where you get like errors, exceptions, and also where you get unpredictable circumstances. So you might run your program and you don't get the output you're expecting. So you're expecting, oh, you put in 1 plus 1 and you get 2. But you run your program and you get 3 or you get 4 maybe, and you're like, how is this happening? There must be a problem. Well, really, most likely it's on your end. So you want to go back and just make sure you are telling the program exactly what you want it to do, because programming languages and computers are very smart in that they can do operations really fast, but generally they don't make assumptions about what you mean. So to you, it might be obvious what you mean, but the computer's not going to assume that this is what you mean. Okay, we're going to do this. It's going to do exactly what you tell it to do. So you're going to encounter plenty of both errors and exceptions in your Java career, so don't be intimidated by them. All right, so after this, we are going to be able to get coding. So what do we need? So first, we're going to need a Java runtime environment and a Java development kit. So if you're on Windows, you can just go to the Oracle website and you can download this. If you're on a different platform like Mac OS or you're on Linux, you can download this as well. And there's also Open JDK. So you can simply download Java JDK, and this will have all the Java components that you need to program. And it might already be installed, so it's always good practice to search your computer, see if it's already on there. And then after that, we also need an IDE. So really, a lot of people have different preferences, but your choice of IDE is really trivial. There's a lot of different IDEs you can use. I will be using Eclipse for all these videos, but another good option is NetBeans. It really doesn't matter what you use. Also, if you don't like IDEs, you could also use a text editor. Just keep in mind, if you use a text editor, there are going to be some limitations, and you're not going to be able to see the errors you write until you run your code, and you're also not going to be able to write your code and run your code in the same place. So once you have a Java development kit, a JDK, and a JRE, and they come together whenever you download Java JDK, and you have an IDE, that's really everything you need. So I hope this session was informative. If you would like to learn more about Java programming, check out our programs at rootfabric.com. Thank you.